In this session, I would like to talk about IO organization. Mainly, we will be focusing on how data will be transferred between these IO devices and main memory. Okay, that is the story. So, this is your main memory, and let's say this is your processor, and these are the various IO devices. Example of IO devices are like keyboard, which sends input, and monitor I can take, right, and disk. Let us take your monitor, which only takes output. That means data will be transferred from main memory to monitor. Similarly, data will be transferred from keyboard to main memory, and data is transferred between disk to main memory and main memory to disk. So it's a two-way, right? So one common organization is having a bus between these devices like this. Keyboard, disk, monitor, all are connected to this main memory. Okay, and processor supervises the data transfers between this keyboard and main memory, disk and main memory, everything. Okay, so that is the role of your processor. One important thing we should discuss, how this data transfers will be supervised. First of all, you have multiple devices, right? Then whenever keyboard wants to transfer the data to main memory, how that will happen? For that, already we have seen a IO, that is called program driven IO. Already I taught that, and we have already seen interrupt driven IO. In interrupt driven IO, so any device which has data, example, let's say keyboard has data and it wants to transfer to main memory. So before that, first of all, it will take the data from the user, right? By that time, CPU will not be wasting its time. So keyboard independently prepares its data. Once data is ready, then keyboard is going to send an interrupt signal to CPU. So that is the point where CPU starts executing the instructions, correct? Now this is your main memory. In main memory, already I told you, there will be a portion where there will be interrupt service routine for this keyboard. Okay, so interrupt service routine for keyboard. Whenever this interrupt is generated, we have to design our hardware such a way that automatically the processor's control, currently whatever it is having, that means program counters value, should be updated to the starting address of this interrupt service routine, example 100. Such a way we have to design the circuit. Okay, then we say that we are using interrupts. So whenever interrupt occurs, finally keyboard processor starts executing the instructions. Because of that, automatically what happens, this keyboard will be served. So serving keyboard is nothing but taking the data from the keyboard and transferring to this main memory. Understand? So for that we will be using bus. So this bus is nothing but you can imagine it like some set of lines through which you can send the data. So this bus will have data lines which carry your data. Second one, some control lines for designing the otherwise deciding the direction, right? Control lines are used for deciding the direction, data transfer from main memory to keyboard or keyboard to main memory, and some other stuff, whether keyboard is ready or not. Of course keyboard is ready, and some remaining things. Okay, it depends on your device, right? So control lines we use to control the operation, and data lines for sending the data. All right, sometimes we will be having address also, right? So address lines also will be used for specifying the address. Example, let's say I want to specify this keyboard's address to processor, then maybe I can use address lines. Okay, so we don't require much details, you just understand the concept that we need this bus. Okay, second thing, so here, sir, how these interrupts will be generated if there are multiple devices? How these multiple devices are going to generate interrupts? There are so many ways. Already we have seen how parallel, otherwise simultaneous interrupt generation possible is through polling. So how this polling scheme works, I will tell you. This is your device 1, device 2. I am talking about how your processor is going to detect the interrupt. D1, D2, D3, D4. This is your processor. Okay. This is your processor. Every device will be connected like this. Okay. D1, D2, D3, D4. Maybe through interrupt line. Okay. I can say like this. So this is interrupt line. There is only one common line. You can follow this organization. Otherwise, so every device will be connected to this interrupt line like this, so that any one of them interrupts the processor. So this int line will be off on. Okay, so that processor will understand that there is an interrupt. Try to understand, whenever there is a interrupted d1 creates sends a signal. Whenever d2 has an interrupt, d2 sends a signal finally. So there will be an or logic. Because of or logic, either d1 or d2 or d3 or d4, I am not showing the circuit, we are just understanding in high level. Okay, so low level circuit we have to design, but I am not talking about that. So d1 d2 d3 d4, understand the story, that is enough for us. So d1 d2 d3 d4 can send a signal at any time. So anyone sends a signal, that will go like this, and it will simply disturb this processor, so that processor will take immediate action. So whenever interrupt occurs, so but in this model we are not specifying which device is causing an interrupt, right? Then processor will do polling. What it will do is, it will come to every device and it will check their interrupt enable, I mean interrupt, maybe there will be a separate bit, I can say. So it will check, it will somehow poll it. That means it will ask device number 1 through some registers, my dear d1, did you create any interrupt? Otherwise, D2, did you cause any interrupt? In that way, every device will be asked. If multiple devices, sends a signal, what happens? We'll see. Example, let's say D2 wants interrupt and D3 wants to interrupt processor. Then what happens? Interrupt signal will be generated. So processor will come to D1 and it will ask, did you create interrupt? No. D2, did you create interrupt? Yes. Then it will not ask D3 and D2 will be served first. Okay. Then this D2's bit will be made 0. So that's it. Sir, then we have a question, because both D2 and D3 created interrupt, right? Then only you serve D2, but D3's bit will be still 1, right? So what happens is, still this after serving this D2 also, then processor still will have this interrupt signal high, so that again processor will start polling. Again it will poll D1 D2. This time D3's bit will be 1 and D3 will be served by going to appropriate interrupt service routine, right? So after that, once D3 is served, then this bit will be made 0. So this is one method called software polling, right? So using software polling we can do it, right? We have to have separate program for that. Okay, now the problem with this software polling is, unnecessarily you are wasting the processor's valuable resources, correct? That means time. Unnecessarily processor is busy lot of times questioning d1 d2 d3, right? So that's why this polling unnecessarily wastes the time. Okay, so we have an other alternative. Of course there are a lot of other alternatives. One important alternative is, and one more thing, in polling there is a starvation, right? What is that starvation? Example, let's say these devices are connected like this, D1, D2, D3, D4, and the polling approach is like this. Always the polling is polling like this, D1, then D2, then D3, D4. In that way it is polling. Then the device D4, though it has a lot of interrupts, still what happens? Then D4 will not be served immediately, correct? If there is no priority for D1 or D2 or D3, otherwise D1, D2, D3 won't create any interrupt, then only D4 will be served, correct? So D4's fate depends on D1, D2, D3, right? So lot of times D4 may not be served immediately, that's why it gets starvation, right? That means indirectly you are giving priority to D1, then D2, then D3. So in priority based systems, generally there will be a problem called starvation. Here also there is a starvation, right? And one more thing I would like to say here, you are ensuring the priority. That means what you do is, if you have very important device like disk which has to be served immediately, if you compare with keyboard or monitor, let's say, then connect disk first. That means poll disk first, then later, let's say keyboard is not so important for you, then poll keyboard in the last. In that way you order your devices to be polled, so that we can have a particular priorities, right? But still starvation exists for other devices which doesn't have much priority, right? Now Second model is we have to connect them in a daisy chain model. This is a software hardware approach, daisy chain. So what is this daisy chain is? So this is your processor, okay. Now these are all various devices, okay. So every device is connected to this again interrupt line, same thing, okay, like this. So they will be connected like this. So whoever interrupts, there is only one line, interrupt line. So whoever generates or creates an interrupt, then processor will understand that, okay, through this line. Once CPU feels interrupt at any point of time, and one more thing here I will tell you. Example, let's say by that time what CPU is doing, it is executing an instruction, right? So you know that instruction execution has a lot of phases, right? Let me take our the regular model: fetch, decode, execute, write memory, and write back. What I want to say is, so each stage generally constitutes one cycle, right? Now currently let's say you are in execution stage, processor. By that time suddenly keyboard created an interrupt. Then should processor take it? No, actually processor should not consider this signal at by that time, right? What that processor should do is, the processor should be designed such a way that the signal should be taken only after end of this clock cycles. That means what? After write back stage. That's what I would like to say, because we have to complete this instructions execution, right? So once you complete this execution, then we take the interrupt. Otherwise what happens, if you are in between, example, let's say you are executing the instruction, you are in half, right? When you are in half, then if you go to interrupt, then what happens, this instruction will not be properly executed, right? You are in between, correct? So we have to complete this entire instruction, then later we have to take the interrupt. You remember that, okay? Otherwise you get unexpected results, right? Example, let's say you have an instruction called storing the data into main memory. Assume like that. Let's say you are storing the data into main memory. For that you have calculated address, everything. Then suddenly interrupt came, then you went. Then after that, coming back to exactly this point will be difficult, correct? That's why what we do is, we simply complete this instruction so that we'll have one safe point, so that later once interrupt is serviced, then we can go to the another instruction easily, right? So example, this is I1, this is I2. When executing I1, if interrupt comes, complete it, okay, most of the times. Then after that, go to interrupt and execute the interrupt. That means execute interrupt service routine and come back. Then happily I can start at I2, correct? If you are in between I1, then you will not have clarity what you did and what you have not, right? That's why it is very difficult to remember the details about half of the instruction, rather than remembering the details of total instruction execution, right? That you should remember. Next, so you have keyboard, let's say, again monitor, hard disk, everything, other device, D4. So in this model, so this is called daisy chain. It is like again polling model, but we don't poll. What happens is, so one signal will be sent to processor, okay. So whenever any of these device generates an interrupt, then processor is going to send acknowledgement, okay. Assume that, let's say, interrupt is accepted, right? So it will send this signal to everyone. So then keyboard won't send that acknowledgement to this monitor, hard disk, and everyone. So you can imagine like this. So zero signal will be sent, so that still these devices who send interrupt, they will think that still processor is not ready to acknowledge us. So now keyboard is acknowledged. Once keyboard is acknowledged, keyboard is a device, it will have some device address. So that device address will be sent, okay. So there are two things: either keyboard's address will be sent to the processor, so that processor can serve this keyboard. Otherwise directly the interrupt service routines address will be sent directly, okay. So that means that is vector, right? Interrupt vector. That interrupt vector will be sent to processor. For that you will be having extra lines. So through the extra lines, that address will be sent finally, so that processor will serve the keyboard. Once processor serves the keyboard, then what happens, still this interrupt line will be active. The reason, other devices also wants to have get serviced. Example, let's say monitor also wants to get serviced, but already keyboard and monitor both sent interrupt. Now keyboard's interrupt has been served. Okay, then it will, what keyboard will do is, keyboard will make this signal 0, so that there will not be any effect on this interrupt line, so that monitor, still monitor is 1, right? So because of this monitor's voltage, then again still processor feels there is an interrupt, then again it will send an acknowledgement. Okay, this time, so that is signal 1. Then slowly 1 will be propagated, but this time keyboard already got serviced, right? So keyboard doesn't have any upcoming interrupts, so it will simply send that one to monitor. This time monitor will be served. Okay, see this situation where everyone wants to get serviced. Okay, that means everyone has interrupt 1 1 1 1, so they send signal 1 everywhere. Okay, so this is, let's say, OR gate, so that at least one of them is 1, then this interrupt signal will be enabled. Okay, such a way we have to design. So now first, because interrupt line is 1, then processor sends what, acknowledgement, so it will be received by keyboard. Then monitor and hard disk and this other device will not receive, because keyboard will topple it, right? Keyboard will send 0 to everyone. That's why they will keep their 1 as it is, but keyboard makes this to 0, and keyboard sends interrupt service vector, so that processor can serve it. Okay, remaining details are not appropriate now. So then later what happens, still this interrupt signal will be 1, then in the next cycles processor will serve monitor and this bit will become 0, then after that hard disk will be served, then this bit will become 0, then D4 will be served, this device will be 0. Again there is a priority scheme, right? So this daisy chain model is again a hardware model. Okay, so this hardware model is also priority based model like polling. One more important information what I can say is, so here also there is a starvation, right? This device 4 will starve, right? Yes, in every priority based model there will be starvation, unless if you dynamically change the priorities, right? So if you physically construct this kind of circuit, then definitely this device which is not close to processor will starve, right? So who is close to processor will get the more priority in that way. So by observing, and one more thing, by your requirements you can prioritize the things. Example, hard disk should have lot of priority, so what you do is you keep hard disk closer to your processor. Such a way we have to design this system about interrupts, right? Finally, so we have seen interrupt driven IO already, and this is helping circuits. If you come to hardware level, so in the hardware level, so this is the circuit which is going to help your interrupt driven IO. Okay, now let us focus on this direct memory access. Before going to direct memory access, one more thing I would like to talk about, this bus. Since there are multiple devices which are using this bus, right? At any time, who have to acquire this bus is the question, right? When multiple devices wants to communicate, otherwise wants to send the data to main memory, then to whom bus should be given is a question, right? So for that, to avoid the chaos, so there will be a bus arbitration circuit. Remember it. Okay, what is this bus arbitration circuit's duty is, this is a circuit when you have multiple IO devices, to have the control over the bus, everyone will send a signal to bus arbitration circuit. Okay, now this bus arbitration circuit will decide whom should use the bus in that way. So this bus arbitration circuit will be important. Understand? So when there are multiple IO devices, everyone will send their signal like bus request. They will request the bus. Okay, when they have simultaneous access, that means at a time if they want to use the bus, then they will send, because we have a common bus, right? So somehow we have to fix this bus to someone, right? That's why keyboard, disk, monitor, everyone will send bus request signals. Then bus arbitration circuit will send a signal called bus granted, so to only one, depends on the hardware circuit which you design. Okay, so you can send you can design this kind of daisy chain model or anything. I'm not going to discuss the details, but so finally this bus arbitration circuit, based on its system, how it is designed, it is going to decide one of the device to take the control over bus, then later such device can use the bus. Remember it. Okay, now with that concept we learn direct memory access. So why direct memory access? Already we have program driven IO, interrupt driven IO. We know that interrupt driven IO is better than program driven IO. But why direct memory access? Now I will tell you. Let us recall interrupt driven IO. So you have a keyboard, okay, and this keyboard wants to send the data. It has some data, let's say X. Then this is your processor. Actually, what happens in interrupt driven IO? Okay, now we don't see the circuits related to this one. Directly we understand the high level idea. So keyboard will send a signal, right? It will send an interrupt. Assume that, let's say, processor finally accepted this interrupt. Then processor will come here and it will, so through the instruction, there will be keyboard generates interrupt service vector also, right? Keyboard says that, my dear processor, this is my, interrupt service routine here at 100. Please go there and serve me. So there will be some instructions here. If that instructions are executed automatically, that instructions will direct how keyboard should send the data to process, main memory, everything. Okay. So because of this interrupt service routine execution, finally keyboard sends the data to main memory. Understand? So here in this interrupt driven IO, finally CPU's time will be saved rather than every time checking whether keyboard is ready or not, because keyboard is very slow device. Already I explained it, correct? So what is my suggestion is, if you want to recall program driven IO and interrupt driven IO, then please attend my basic IO lectures. Okay, there is a section called basic IO. So you go through that basic IO section, and especially program driven IO and interrupt driven IO. Okay, after that you come back here, right? So now I am going to show the difference between interrupt driven IO and direct memory access. What is direct memory access is, here also you are using CPU unnecessarily. Where? I will tell you. So once keyboard has data, then keyboard generates interrupt, right? Then after that, by that time you are not using processor seriously. But once you have data, then processor, what you do is, so processor is executing this interrupt service routines, right? So whenever processor is executing this interrupt service routine, then data will be transferred. But all these instructions are unnecessary. Why? If you have a better model. What is that better model? I will explain you. So in that better model, we will be proving that this executing interrupt service routine is also unnecessary, so that CPU's involvement is not required. How you see? Generally, what is our goal in the hardware level? You see, you have data, right? Okay. So let us assume that we have plenty of data. If it is only one character, then there will not be any problem. We can go for interrupt driven IO. But when we go direct memory access, I will tell you, you have lot of data, okay, huge data. Example, let's say you have 256 bytes of data, and you want to send all the 256 bytes to main memory through interrupt driven IO. So what happens if you really want to send 256 bytes of data? Let's say this is some hypothetical device. It is sending byte wise, okay, byte 1, byte 2, byte 3, everything. Whenever it has a byte, it will interrupt the processor. Now see the situation. So I will try to connect it with some story. So this is your processor. Whenever there is a data available for a device, then what the device will do is, it will send an interrupt. Then processor will go to interrupt service vector, and it will execute these instructions, which will cause this byte to get transferred to main memory. In that way, because of this instruction execution, assume that there are 10 instructions whose execution finally makes what? Because of this instructions execution, this data will be transferred to main memory. Remember it. Now if you have another byte, then again, because you have designed your system such a way that, so far we assume that we were sending one byte, correct? To send one byte, we did all this stuff. What if you have another byte? Simply create another interrupt, then processor will execute again this interrupt service interrupt service routine, then again second byte will be transferred, right? So finally through the program, of course, you will be, that is interrupt service routine, we will be sending all the 256 bytes. Assume that, let's say, these 10 IO instructions are taking 5 nanoseconds. Okay, each one 5 nanosecond. Then that entire interrupt service routine program is taking 50 nanosecond. So I can say that if you have 256 bytes, to transfer each byte you need 50 nanosecond. Why? We will see. 9 o'clock early morning, processor is not at all useful for you. That means you are not using processor is busy, okay, doing other instructions. Now you have suddenly data, okay. So whenever you have data, then you simply call processor through hardware mechanism. Already we have seen daisy chain, right? Maybe that you can use, otherwise polling, whatever. Quickly assume that that time is negligible. So very quickly we identify the process, I mean we just say that processor, I am ready. Then processor will go to this program and it will execute it. Executing this program is nothing but transferring 1 byte of the data. I can say that the overhead or the amount of time you used CPU for your work is only here, right? When this interrupt service routine is executed, that overhead is 50 nanosecond, right? After that you will be transferring whenever you have data. Assume that, let's say, once you send 1 byte of data, okay, then you need a gap. Okay, you don't want to send immediately because your device is not ready to send another byte, so there is a delay. Example, let's say for 5000 nanoseconds there is a delay. 5000 nanosecond delay is very negligible for a human being, but for processor is it's a huge time. Within that time your processor can execute other programs instructions if operating system has multi-programming environment, okay. So that's why you see here, assume that, let's say, your processor is used for executing all the programs or multiple programs at a time. Then you see 50 nanosecond one instruction time, right? Then in 5000 nanosecond your processor can execute 100 instructions, right? So that your computer's throughput will be improved, right? So that's why what is my suggestion is, so this interrupt driven IO is definitely better than program driven IO. In program driven IO we will be seriously busy waiting for device, even processor also waiting outside this house for and it will ask device 1, my dear device 1, are you ready, are you ready, through its instructions. So your CPU is going to ask, my dear device, are you ready, are you ready. So CPU is also busy asking that question, right? So that's why to avoid that we invented this interrupt driven IO mechanism. But in this interrupt driven mechanism also we will be using the CPU for 50 nanosecond. Now you see how much time we will be using this CPU in this interrupt driven IO. If you see, first of all we transfer 1 byte, so we take 50 nanosecond, right? Each instruction takes 5 nanosecond, 50 nanosecond. After that we have another byte. Whenever there is a byte, sir, what about this 5000 nanoseconds? This 5000 nanosecond time CPU is not busy, it is doing something else. Again you have a data, then we have to interrupt it. Whenever you interrupt it, CPU will come and CPU will send the data and it will go away again. It will not wait for you. In that way, for every 1 byte we will be using CPU only for 50 nanoseconds of time, right? So after one more byte, again CPU will come and it will execute interrupt service routine. So this is interrupt service routine time, so only 50 nanosecond. In between byte transfer, if there is a delay, CPU will not wait, CPU will do other work, correct? Because CPU will come to you or your program only if your device creates an interrupt, right? That is about the power of interrupt driven IO. Now we will see the problem with this interrupt driven IO. Still, if you have huge data like 256 bytes, then unnecessarily 256 into how many nanoseconds, 50 nanoseconds of time you have to waste, right? To avoid that, direct memory access is invented. So we will see how this direct memory access will avoid that problem. If you see carefully, so in interrupt driven IO generally what is happening, this is your CPU, right? So this is your main memory and this is your device, right? So whenever device has data, then it is disturbing the CPU, right? Then that CPU indirectly is executing interrupt service routine. So for the devices which sends only 1 byte periodically, there will not be any problem. That's okay to go for interrupt driven IO. But there are some devices which are block devices. Okay, so when there is a block device, that block device sends huge data. Okay, so maybe that device can send some block of data whose size is 512 bytes. Imagine this situation. Example, hard disk. Generally, data transfer from hard disk to main memory is in blocks, and the block size is very huge. That is around 512 to 1024 bytes. In this situation, then if you use CPU for this data transfer, unnecessarily your CPU will be busy, correct? Because every byte should be taken by your CPU and it has to be transferred to main memory. So it takes lot of time. So that's why direct memory access has been introduced. In direct memory access, what we do is, this is your processor. There will be a small controller called DMA controller. Okay, so DMA controller. How things works, we'll see now. So in direct memory access, hard disk first of all will call this CPU by saying that, my dear CPU, so these are the details. So this is my data, 512 bytes of data, and this is the location where data is residing, and this is the destination address. That means source address, destination address, everything will be negotiated by through processor. So processor understands where to send the data. Okay. Now after that, what CPU will do is, rather than wasting its time, CPU will give the control to DMA. Okay, so what happens is, really CPU will give, so see, if you focus on DMA controller, what is DMA controller is, DMA controller will have some set of registers again. Okay, one register can remember the count of the data. Okay, data count, and one is for address, correct? So maybe address. In that way, various components, these two are important. That means this DMA controller can take the address where in the main memory data to be stored, and the data, how much data, and the device address also. In the device, where is the address, data address, I can say. Okay, so let us say data address. So all these details we can store in the DMA. What your processor will do is, whenever hard disk is ready, then immediately hard disk will send the interrupt, then processor will serve that interrupt like this by allotting the work to DMA. My dear DMA, you have see this count data register, right? In that I write 512 bytes. That means you have to transfer 512 bytes. Then address is in main memory, starting address 100. Then in hard disk the starting address is, let's say, 500. In that way everything will be provided. For that CPU will intervene. CPU wastes its time, yes. After that what happens, then your CPU will be removed from the control. That means now DMA can do this data transfer. DMA also can, example, let's say whenever CPU is using main memory, how it will use, for that appropriate signals will be generated, right? Whatever the signal CPU generates generally to do some work, everything will be mimicked by, otherwise repeated by this DMA controller. DMA controller also knows what are the control signals required to send the data from some device to main memory. It's like a small processor. Okay, so that now this main CPU is very happy because now its intervention is not required. Okay, in general cases, for every byte transfer CPU should intervene, but in this model now CPU only initiates the transfer. After that, direct memory access DMA controller will start working. What it will do is, it will go to main memory, it will communicate with main memory. My dear main memory, so see, and one more thing, DMA controller is also connected to bus in that way. So now see, through this bus data will be transferred to main memory. Okay, so where memory location 100, into the main memory location 100 we send the data, then 104. In that way all that 512, sorry, 101, in that way all the bytes will be transferred. Okay, this is a way direct memory access will work. If you see, when you are transferring the data between DMA controller to main memory, CPU is happy. Why? It can do its extra work, other work. Other work means, sir, maybe it can execute other programs or other instructions, correct? So let us forget about other programs and everything. In our computer organization, for us everything is instructions, right? So it doesn't bother us whether it's our program or another program, right? I1, I2, I3, I4. So what I want to say is, if Any instruction, when CPU is executing any instruction, suddenly this kind of hard disk requirement, that means data transfer between hard disk to main memory, because of any of the reason, then CPU will, initiate the action. Otherwise, CPU will initiate that process by telling the DMA all these things, like what is the data count, everything. Then later it will continue with its instructions. Here there is one more thing. Your, CPU will not store any data. That means, generally in interrupt driven IO, whenever to serve interrupt service routine, then what we do, recall, whenever interrupt driven IO is executed, your CPU has to save all its data, because interrupt service routine is also another program, right? Whenever you are executing this program, the current program should be saved. That is what I want to say. But here the current program need not be saved. That's why it's quick. That means work allotting the work to DMA controller is very quick. Why? Simply give these details, but you don't save your program's data. Why? Sir, what if this DMA controller disturbs? It never disturbs. It's not a processor like this. So this won't execute instructions. It's a kind of hardware. So it will just work on this main memory, right? So that happily you can execute instructions. Sir, I have a doubt. What if this instruction wants to communicate with the memory? Because example, let's say that instruction is loading some data into a register R2 from main memory of some 700 something. Then no problem. Assume that, let's say, currently this 700 is not used by this DMA controller. Then I will say one thing. Why you want to go to main memory? We have a cache, right? So that's why CPU can continue execution of remaining instructions by going to cache. Understand? So we never require main memory. Sir, sometimes cache miss occurs, right? If cache miss occurs, then we have to consult you also. That means this processor also wants to consult main memory. Then there is a contention, right? DMA wants memory, you want memory, right? Then who will be given memory? Right? There is, then definitely CPU has to wait, right? Yes, there is such problem. But our assumption and our hope is 90% of the time cache hits, right? Then at that time you don't require memory. Then hard disk to this main memory transfer will be done by this DMA controller. Then CPU can parallelly execute other instructions. In that way throughput will be automatically improved. So finally the goal of direct memory access is avoiding the CPU. Otherwise, unnecessarily, we are not wasting CPU for this kind of data transfers, right? Huge data transfers. Otherwise, unnecessarily your CPU will be busy sending this data hard disk to DMA. So at that time it cannot execute other programs or other instructions, so that speed will be reduced, right? So definitely because of DMA, speed up of your computer will be improved. Now one essential thing you should understand, sir, once direct memory access is done, sir, finally your disk controller or your DMA controller transfer data which is desired 512 bytes to main memory. After that, how CPU will understand that? So immediately this disk controller is going to create an interrupt. It generates interrupt by saying that, my dear CPU, my work is done. Now still you have any problem, sir? Why we have to tell that? Why? Because maybe in the process of sending the data there might be some errors, right? So it's quite complicated to understand, but just understand like this. Sometimes DMA controller cannot complete its task. Then CPU, whenever once it is done, DMA is going to generate your DMA controller is going to generate an interrupt. Whenever that interrupt comes, CPU will just tally, otherwise compare the work. It can check everything is good or not. Okay, if it is not good, then again it will do the remaining work, like whatever. It depends on the situation, right? So this is about direct memory access. Let me summarize. First of all, device will, whenever whatever the device which wants this kind of huge data transfer, bulk transfer, it will simply interrupt that CPU. Then CPU will understand the problem, how much data to be transferred and what are the source and destination addresses, everything that will be given to DMA controller, which is a small processor. After that, CPU will be busy doing some other instructions. Okay, now normally, now DMA controller parallelly, so CPU while executing its addition, subtractions, multiplications and cache access, loading, storings, everything, then this disk controller seriously busy doing the data transfer between IO devices and main memory. In that way, so two processors I can say are working parallelly to improve the throughput. Okay, that is about direct memory access. Now we'll see one numerical problem to understand how much benefit you get because of direct memory access. Okay,